So now we are going into more detail after the overview that we just heard from Sudhanshu. And what we are focusing on now is the message, the GPS message. Basically what I'm going to talk about is what is the message that is actually transmitted from the satellites, and second, how is it transmitted. So just as a very basic review of what you already heard, there are carrier waves. There are two carrier waves, L1 and L2. And then on those carrier waves, there's a code riding on it, and there's the P code and the CA code. Basically, we have what type of information do we have available for positioning? Well, we have two waves, two carrier waves, and two different codes. So each of them have different properties. Not all of them are accessible to civilian users. So what we are going to do now is go into the details of what each of them do. Each of the carrier waves carries a PRN, a pseudo-random noise code. Why is it pseudo-random noise? Well, it basically sounds like white noise. Like if you turn on your radio, it sounds like white noise, and sometimes you hear music, right? So the white noise is basically what it would sound to you, because you can't really distinguish a message in there. But there is a message in there, and it's predetermined, and that's why it's pseudo-random, because it's not really random. And those pseudo-random codes, there are two different codes. One is the P code, or the precise code, is actually superimposed on the two carrier waves, L1 and L2. And it is for the precise positioning service, PPS. And then there's the CA code, which is the course acquisition code, and that is only on the L1 carrier wave. The P code is basically one bit of code. The CA code is different for each of the satellites. So each of the satellites has its unique CA code. It's also referred to as a gold code, like a gold standard. So each satellite is identifiable by its own unique CA code signal. What is that signal or that message is actually used for? Well, a lot of different things. The main reason why we actually use GPS, which is it must be usable for calculating ranges or distance. We'll see how that's based on time in a minute. We need to know where the satellites are. Then we need to know where the satellites were and where they are going, basically the orbital plane. So that's another key information. Then time. Sudhanshu mentioned a little bit the importance of time. So we need more accurate time, which also is synchronized. Then we must report error status. For example, is that satellite in service right now, or are there any other problems? And then atmospheric corrections. We'll also need some information on the atmospheric correction. Now, all of these information packets are actually part of the navigation broadcast message. Now, how is that all that information actually transmitted? Well, as in all digital systems, it is zeros and ones. So zeros and ones, the binary code. Now let's step back for a minute and let us take a look at the core principle of GPS, which is actually time and the waves that actually transmit the signal. What we see is that there are oscillators that keep actually chopping off at an electromagnetic energy beam. You can actually determine very exact time and very consistent time intervals. These consistent time intervals are then used to create that wave, the carrier wave, and you use it based on the time. And how is that connected? Well, the wavelength, lambda, is actually equal the speed of light, corrected for the atmosphere, that's why it's CA, divided by the frequency. So, what does that tell us? Well, let's take a look at the L1 carrier wave. We know, for example, that the speed of light is approximately 300 meters times 10 to the power of 6. Then the frequency is about 1500 megahertz, as you have already heard before. Now, in order to calculate the wavelength here of that one wave, what we need to do is 300 divided by 1500, and that's approximately 0.19 meters or 19 centimeters. So each of this wavelength here, of that L1 carrier wavelength, is 19 centimeters. We'll come back to that importance a little bit later when we talk about how we can actually track. So that oscillator is operating at a frequency of 10.23 megahertz. And then, for example, the L1 and the L2 carrier waves are just multiples of that frequency. So, for example, L1 is 154 times the 10.23, and that results into our L1 frequency, which is actually the 1575.42 megahertz. L2, the second carrier wave, very similar, but it's multiplied by 120. The implications of this is that we have two different frequencies in each of the two carrier waves. So L1 and L2 operate at two different frequencies. That is very important for atmospheric corrections. The P code, actually chips or bits of information, they are generated every microsecond. 10.23 million bits of information per second. So bit is basically a 0 or 1. So you get 10.23 million 0 or 1s per second. That is the P code. Now, the CA code chips occur at every 10th P code, which means it has basically, it's at a slower rate. It's at the 10th of the speed of the P code. And you can only pack about 1.023 million bits of information in 1 second. So the 10th of the P code of the precise code. And that is also the reason why the P code actually allows for a more precise positioning, because you have more bits of information and you can determine in which bit, at which bit you actually are. Similar if I would say 0 or 0, right? You can determine the time when I said 0 way better if I say it faster. So that bit of information that's 0 or 1, that's basically the time interval that it takes. And that's where you can narrow down at which point in the code you actually are. So if you can pack more information in the same time interval, then you will be more precise at determining where you actually are, at what time you actually received that 0 or that 1. Or a short summary here of the two codes, we have the CA code, which is generated at about 1 million bits per second, and it repeats itself every millisecond. So every millisecond you start a new CA code. And that whole signal, similar as we calculated it before, how long is that signal? It's about 300 kilometers. So 300 kilometers of signal actually come in every millisecond. Okay? And that has information at a rate of about 1 million bits per second. Now, the P code has about 10 million. And the P code is on both the L1 and the L2 frequency. And each satellite repeats its portion of the P code. So the P code is basically chopped up between all the different satellites, and each satellite gets one portion of the P code. So it repeats each portion of the P code every 7 days. So how long would you have to wait in order to know when does it start again? So how long do you have to wait, basically, like if you're watching a movie and you want to catch it from the beginning, right? So how long do you have to wait in order to catch it from the beginning so that you know where you are? A week, 7 days, right? So there needs to be more information that tells you where in that code you actually are, because you can't wait. You know, it's not feasible to stand out there for a week just because you have to wait for the new code, right? So there's additional information that is transmitted that tells you where in the week you are. And then this code is renewed about every 37 weeks. Everybody okay with that? Important CA code, unique to each satellite, repeats every millisecond. P code, more precise, more bits of information, repeats every 7 days. Okay, so now that we have a carrier signal, L1, L2, we need somehow modulate the information of the code onto that wave. The way it's done is actually by a phase shift. First of all, we start out with zeros and ones. Zeros and ones don't really lend themselves to phase shift, so what we do, we translate that into -1 and +1. Then the -1s and +1s can be phase modulated onto the carrier wave. Here, for example, we have a -1, and here we see that the carrier phase does not continue as expected, but it has this jump here, so it goes right down here. So it's basically multiplied by -1. So instead of going into the positive, it's going into the negative. Similar as you would expect it to go into the negative, if you multiply it by -1, it goes up into the positive. So these jumps here, these phase shifts, occur at every zero of information, or translated -1, right? But at every zero, basically, you have one of these phase shifts. Now this message now, this carrier phase is now modulated with that pseudo-random noise code, which is the 0 and 1s. Once in the receiver, then you can translate it back to zeros and ones, and you get all the information that you wanted, as all the information in your computer is 0 and 1s. We said on the L2 signal, there is only one pseudo-random noise code superimposed on it. However, on the L1 signal, we have both of them. We have the CA and the P code on top of that L1 carrier phase. How does it actually work? Well, they are 90 degrees apart. Remember in the beginning, we had that wave, and we said in the beginning it's 0 degrees. On top of the first one, it was 90 degrees, 180, 270, and 360 degrees. Now, just imagine that every 90 degrees you would use one signal, and every 180 degrees or so, phase shifted by 90 degrees, then you actually could tell which signal starts where. So there's no interference. There's enough space on that wavelength that you can put two codes on there. That's basically what it says. And the way how it's determining which code it is by using which phase shift it actually modulates. Now that information is not just poured onto you, it's actually provided to you in 5 subframes. So there are 5 subframes, and the next figure actually will show it more detailed. And each of these subframes now carries specific information. Specific information that is, again, the navigation message, and has to do with clock corrections, ephemeris data, we'll go into detail what that means, atmospheric corrections, time differences between GPS and universal time, and data on where to find other satellites. So that's basically the information that we discussed before, all that information that we need to transmit from the satellite to the receiver. Now how that actually works with the subframes is right here. Just imagine that you have these 5 different subframes. Each subframe is 300 bits of information, which takes about 6 seconds. And then one frame is actually made up of 5 subframes, or 1,500 bits of information and 30 seconds. As you can see, for example, the first subframe carries information on the clock correction. The second and third carries ephemeris data. The fourth and fifth carries other data like ionosphere corrections, time, and the fifth frame actually carries almanac information. Now, with these two subframe 4 and 5, we need to pack much more information than we actually pack into the first 3 subframes. So once we transmit a block of these 5 subframes, we'll actually only transmit some of the message here, because it actually needs 25 pages or 12.5 minutes, which is way more than one block of 30 seconds. So basically, multiple of these blocks make up these subframes 4 and 5 are not complete. Only the first 3 subframes are complete. These ones here are chopped up into multiple blocks. We'll come back to that. So the subframe 1 actually uses time and clock corrections for each individual satellite vehicle, SV. That is very important for our correct positioning. Then by time differencing, we can actually track the start of the signal, which we'll cover in a minute. Subframes 2 and 3, that's basically where the ephemeris information is all collected. So what is the ephemeris? Basically, it just tells you on which orbit the satellite goes around. And it's all detailed information on that orbit. So for example, the semi-major axis of the orbit coordinate system. Eccentricity, how much deviation from circular? Because the satellite doesn't really go into a circular orbit, but it's more like an elliptical orbit. So the eccentricity will basically give you the ratio between the two axes, like in an ellipsoid. Then the right assonation of its ascending node and the inclination of its plane. That's basically in the previous picture you've seen all these 24 satellites in different planes. That basically identifies exactly in relationship to the Earth where is that plane. Where is its inclination and where does it sit. The perigee is actually the point where the satellite comes closest to the Earth. The apogee would be where it's the furthest. Then the true anomaly is the angular distance of the satellites from its perigee as seen from the center of the Earth. If you want more information on the ephemeris, then please visit the link that's provided to you at the bottom of the slide. But basically what it tells you is the Keplerian elements of the orbital planes of the satellite. And of course each of the satellites have a different orbit. And they are not fixed, so basically you have to upload small corrections all the time that are provided to you from the ground stations. Subframe 4 contains atmospheric corrections. The atmospheric corrections are specifically of interest to single frequency receivers. Sometimes you might hear, you have one frequency receivers or dual frequency receivers. The dual frequency receivers cost more, right? And can receive basically both frequencies. For single frequency receivers, it is very important to get those atmospheric corrections. Why not for dual frequency? Well, because we said that the L1 and the L2 wavelengths are different. So they are differently impacted by the atmosphere that they cross through. So if you have two different frequencies, you can basically get out how much each of them was impacted. If you have only one, there's no way that you can get that information unless you use subframe 4. Subframe 5 contains an almanac and satellite health information. What is the almanac? Well, it's basically some subset of the ephemeris. so that you know where each of the other satellites actually are, so that your receiver knows which satellites to listen to and where to look for them. Then the satellite health information, if there are any mechanical errors in the satellite, you should not use them, or any clock errors that are also transmitted, that's basically in the satellite health information. Now, you've already heard that the GPS system, part of it are the satellites. How many satellites are there? 24 are required for its use, but they're usually up there between 24 and 29 satellites. So some satellites are in use, and some are basically, as I like to say, used as spare parts for the others, right? So they're basically under maintenance, or not yet in use, or they're old and they're being replaced. So pretty much what I referred to before is in frames, subframes 4 and 5, you pack way more information, but you don't want to wait 12.5 minutes all the time. So in order to make use of the first 3 subframes, subframes 4 and 5 are not transmitted in its entirety all the time, but they are chopped up and put into multiple blocks. So then we have also the TLM and the how messages. So what they basically are, they're right in the beginning of each of the subframes, and the TLM is the telemetry word, which basically tells you from the ground segment how much information it updated. Like you heard of the ground segments, right? The 5 ground segments around the world, with the main one being in Colorado. So these ones send information to the satellites all the time that update all the information. So that telemetry word tells you basically how far it is in updating itself. The handover word, and that comes back to the information where we were on the P code. Remember when we said you don't want to wait 7 days in order to get the start, and you need to know somehow where we are in that code, in the P code? That's exactly that handover word that tells you where you are in the P code. So that's basically the information that is transmitted in those 5 subframes, and that's the navigation message. So now, they're basically, as we said in the beginning, what do we have available for that determining the distance task? Well, we have the two carrier waves, L1, L2, and then we have those codes, the precise code and the coarse acquisition code. Now, in order to determine now when that signal left the satellite and match it up with our receiver, we have 2 main ways to determine that. The first one is code ranging or code matching. What do you think that will use? The codes, right? And then we have the second one, which is carrier phase shift measuring. And what does that use? The carrier phases, right? So that's basically our 2 approaches to determine when that signal left basically the satellite. Then we can measure the time it took to our receiver. Then we can measure the distance between our receiver and the satellite, right? That's our big task here. So first we'll take a look at code ranging. So the code ranging basic equation, and please, this is a very basic equation. You have more detailed information in, for example, GPS satellite surveying by Alfred Like. And what that equation actually contains is all these different bits of information like ionospheric corrections, clock errors, and everything else. So this one here is a very simplified and scaled down version of the true equations that are used in your by GPS. So here we have the range, R equals C, which is the speed of light, times the time it took for the signal to get from the satellite to your receiver. So now R lets us then calculate the range, the distance basically between the receiver and the satellite. So what we need to focus on here is the delta t, the time it took for the signal. That's what we want to determine with our receivers. So we want to do that based on the code. So now let's focus, for example, on the CA code, the course acquisition code. That's where to start with, right? So the CA code, basically all the satellites create that CA signal. So that's where we have to start with. Then how do we actually pick out the unique CA signal of one satellite? Well, the receiver reproduces all the CA codes from all the satellites. And then basically it picks up one signal and tries to match it to which satellite it actually is. So how that works is, that would be some basic pseudo-random noise code. For example, the CA signal, zeros and ones, and then we try to match it to another signal that we produce in our receivers. Here, the top figure is, for example, trying to match with the wrong satellite code. So you go through all the different, let's say 24 satellite signals that you produce in your receiver and try to match up with one that you received. Which of the 24 is it? The top one is not a match, so that's the wrong satellite you're suspecting. The bottom one, that would be a partial correlation with the received, between the received signal and one signal that was generated in your receiver. Once you know that, you can actually get it to where you have an autocorrelation, so that the signal matches right on top of each other. Once you have that, it's also called that you attained a lock on the satellite. We have this one signal that we get from the satellite, that pseudo-random noise code. Then we have that same signal which was generated in our handheld receiver. Now, we know when we started it in our handheld receiver. What we need to do now is match those zeros and ones so that they are overlapping or in autocorrelation. What you can tell then is how much time you had to move that one signal, the delta t, how much you had to move that in order to achieve that autocorrelation. That delta t is actually the time it took to travel from the satellite to your handheld receiver. Those signals started at the same time to produce, and then once it is received, you try to match it up and go back in time. How far do you have to go back in time in order to match those start signals? That's your delta t.
In doing all this code matching, is it trying to determine exactly what satellite it's receiving it from?
That was in the previous one. So in the previous slide here, you can see now it was trying to determine which satellite it came from. Once it determined that, you do a partial correlation. Once you have the partial correlation, you're happy with it, and then you go to the autocorrelation, where you basically overlap the signals right away. Now then we can come back to this equation here. The range equals the speed of light times the delta t. Delta t is just what we determined by overlapping those signals. Now, there are still some errors included in that, specifically clock errors. These clock errors can be due to temperature changes, radiation, don't necessarily think about the receiver radiation here, but in space, radiation that the satellite received. Acceleration, how fast the satellite goes, relativity theory, those things. So there are some clock errors in here. These clock errors are not considered yet. Since we didn't consider those, we call it a pseudo-range. So this is not the true range, because there are all these errors in there. What we achieved now is a pseudo-range. So the pseudo range is basically what we determined with the delta t, and we didn't correct that delta t yet for clock errors and so forth. Now let's take a look at those codes. That precise code, which actually has those 12 million bits of information each second. Remember, those finer increments, what we said, allows us, under ideal conditions, to match it up to about 30 centimeters. So 30 centimeters, that's pretty much the best we can ever get with a P code. You know, just using that P code under ideal conditions. That CA code is how many times less information, how wider are each of these bits of information. 10 times more, right? We had 12 million versus 1 million of information, bits of information. So 10 times, we said 10 times less information basically in one of these scales. So if you multiply 30 centimeters by 10, that's 300 centimeters, so that would be 3 meters. So the CA code, basically, under ideal condition, what you can get is about 3 meters. About 10 times worse as with the P code. And that is because there's 10 times wider those information pieces. Now to conceptualize it again, here we have, for example, the CA code ruler and the precise, the P code ruler, which is basically more units of information, or again, in time and in code, the difference would be the CA code, you say 0, 1, basically, right? Stretched out. Or here it would be 0, 1. So you have each of these informations and you have better chances to actually fit them exactly where they need to be. Now, we addressed the code matching. The second option that we had was actually using the carrier phase or the carrier wave to actually match it. Now, where could you see that there are some problems with that? Where would be the challenges in matching those? Well, you know exactly when that code started, so you can match it to a specific code. What do you have in the wave? Absolutely nothing, because it repeats, for example, in the L1, those same 19 centimeters over and over and over again. They're not tagged. You don't know when it started. You don't know when it left the satellite, because they look exactly the same. Those ones are the cyclic ambiguities, because you cannot really determine which wave you actually want to match up. Like with the code, you had those 0 and 1s that were specifically recreated. With the wave, you don't have that. It's basically the same thing over and over again. So that's one of the challenges here. But the way it works is basically you have those 19 centimeters long for the L1 carrier wave that you then try to match up in these different phase shifts. One of them is the receiver, the reference wave, and the other one is the transmitted one that actually went from the satellite to the receiver. Then you try to match it up. But you don't know which of these waves to actually match up, right? So all you can do is those fine corrections. And that's what the better satellite receivers take advantage of. They also have this carrier phase shift that they can actually take advantage of and match it up, and then they're more accurate. Problems again with which one is it. You don't know which one to take into consideration, and that's referred to as the cyclic or integer ambiguity. What else? Well, we just said that frequency travels, that signal travels from the satellite to a receiver. What's in between there? The atmosphere. So that wavelength basically, that signal won't look the same after going through the atmosphere. Right? That will change. So that's another challenge. And what other challenge are we facing? So here basically we're referring to the codes. Cannot tell how many cycles we actually used. And the last challenge we're actually facing is the satellites are moving. Right? So what we have there is a Doppler shift. The Doppler effect, you might have seen it when you see a car or something like this, car racing. When they come towards you, it's going up higher and higher pitch note, right? Coming towards you, once it goes away, it goes and goes deeper and deeper, right? So when it comes to you, or when it goes to you, you have that frequency shift. Now the satellites are always in motion, so you always have that frequency as well. So these are some of the challenges of the carrier phase matching or carrier phase shift in order to determine the accuracy. Or what are the challenges in determining the phase shift? Is it's always the same wave. There's no way to determine which wave you're matching with the one generated in the receiver, because it's always the same thing. Basically, it repeats itself every 19 centimeters. So that was one of them. The other one is when it goes through the atmosphere, it has all these disturbances going through the atmosphere. And whenever you're dealing with something in motion, you have to consider the Doppler shift when you measure its frequency, right? Because the frequency will be distorted depending on whether it comes towards you or it goes away from you.
So the first one, because it's the same wave?
It's the same wave over and over again.
Why is that a challenge? Because it's hard to match it? Or?
It's hard to match it. If I say, for example, these computers in the front here, these screens, right? And I give you another one, and I say match it with that, make it right in the same spot. You don't know which one it is. You don't know which one to match it to because they all look the same. Whereas if you have the code, yes, they look the same as well, but they're 300 kilometers long. Whereas the wavelength is 19 centimeters long. And the other code is, 7 days long. So, any other questions? Okay, then we'll make a 10-minute break and I'll see you again tomorrow.